This is the sixth video in the BattleZips-Noir series. In this video, we're going to jump into the smart contract infrastructure. That's going to involve a look at the custom contracts for the Battleship game, as well as the auto-generated board and shop verifier contracts, which we will then show where we integrate them into the pre-existing infrastructure. Let's go ahead and jump into the code. Okay, so looking at the BattleZips-Noir repo, we have a directory called contracts, and that contains 5 different smart contracts. We have the auto-generated verifier contracts for the board and shop proof. We have a verifier interface, which is a way of exposing the verify function from these verifier contracts, and we'll touch on that in a minute. We have the Battleship game interface, and then finally we have the Battleship game contract where that interface is implemented. But starting off with the verifier contracts, as mentioned, these are auto-generated and they contain a lot of assembly code, which I don't think many of us can say we could write proficiently. But luckily, all we have to do, we can generate the contract via Nargo or through a TypeScript library. But all it needs is that proof we write in Noir, and it will be able to generate this verifier contract. What we're really concerned about from these contracts is the verify function in particular. And this is just a function that takes the proof as an argument through types bytes call data and returns whether or not it's a valid proof, if all constraints are met or not. But obviously, we don't want to look at all this code for both verifier contracts, so we implemented a simple interface for the board and shop verifier that just exposes this verify function and makes it a lot more readable. But moving on to more of the customized contract code, we will step into the Battleship game interface. And looking at the events, there are 6 different events for this contract. The left event is when a player has left a game, but it has not been joined by another player. Otherwise, this would be considered a forfeit, and the player that did not leave the game would be crowned the winner. We have a started event, and this is when a player has created a game and is then joinable by another player. We have the joined event, and this is when a created game has been joined by another player, thus no other players can join after. The shot event, like the name suggests, is when a shot is taken at the other player's board. It emits the X coordinate, the Y coordinate, and the game ID. And for all of these events up here, the buy parameter is, buy parameter is the address of the player who triggered this event, and the nonce is another word for the ID of that specific game. The report event is when a player reports the previous shot that was taken and whether or not it was a hit. And finally, the one event is when a game with 2 players has concluded and either one player has sunk all of the ships, the other player, or a player has forfeited, and the player that has not forfeited is crowned the winner. Moving down, we have an enum called game status. A game can be joined. That's when 2 players have joined an active game and are actively playing each other. We have not started. That's when a game has yet to be created. We have over. That is when a game has concluded. Either a player has left when another hadn't joined, or they had forfeited, or one of the players was crowned the victor by sinking the other player's ships. And then finally, the started status is when a player has created a game, but it has not been joined by another. We're just going to touch on how the game state is stored on the contract. So we have a struct called game, and this contains the participants of the game, the participant boards. These are just going to be Peterson hashes of each participant's board. The turn ID, also called nonce, a mapping of shots where the turn ID is mapped to the shot coordinates of that turn, a mapping of hits, which is going to indicate whether a turn ID has resulted in a hit nonce array, which is going to store the number of hits by each player, game status, and then finally whether or not a game has had a winner. And looking over the variables, the max number of hits that can occur is 17, because that's the total amount of coordinates ships can take up on a board. Game index is the index of the current game, also called the game nonce. Trusted forwarder is something for meta transactions that we're not concerned about in this implementation right now. We have a mapping of game IDs to the game struct, a mapping of the address of a player to whether or not they're in a game or not, and then finally the board verifier interface and shop verifier interface, which are called in different spots in the contract. But that's all that's worth touching on for the interface. Now we're going to hop over to the actual contract implementation and walk through some of the functions there. So looking at the constructor, we take in 3 different arguments here. We take in a forwarder, and a forwarder is just if we want to implement meta transactions. In this version of BattleZips-Noir, we aren't. So this is just going to be address 0 we're passing in. But then we pass in the address of the board verifier and the shop verifier. And we go ahead and assign these to the board verifier interface and shop verifier interface that we import from the verifier.sol file. Looking at the new game function, we take in 2 arguments here. One is going to be the Peterson hash of the board of the person who started the game, and the second argument is going to be that board proof. Now before we continue, we just want to verify that this board proof is valid, so we pass it into the board verifier verify function. If it's not, we revert. If it is valid, we continue by incrementing the current index of the game and then creating a new game struct to represent the game index. And then finally, this function concludes by emitting a start event, but now this game has been created and is joinable by another player. The leave function is a function that either allows a player to leave a game that hasn't had another player join. In that case, we emit a left event, and it also allows a player to forfeit if another player has joined, but they want to leave that game early. We're not going to go over this one in much detail because it doesn't really use the proofs, but going down to join game, we then again want to pass in a board hash and a board proof along with the game index for the game we want to join. And we start this off by, again, just confirming that this is a valid proof by passing into the board verifier. If it is, then the second participant of the game will be assigned to the message sender. Second board hash will be assigned, and then the game status will change to joined. And this function concludes with a joined event, and now the game is no longer joinable to another player. So looking at the first turn function, this is an interesting function and a little counterintuitive at first, because in order to actually have a shot proof in this game, we want to report the shot back, or the previous shot back, when you're then making another shot. So the first shot actually isn't going to have a proof because there's nothing to report back. So this is just going to store the shot data within our game struct and then emit a shot event. But going down to the turn function, this is where we will then be using our shot proof. So this will take in the ID of a game, whether or not the previous shot was a hit, take in the coordinates of the next shot, which is going to generate a proof in this case, and then taking the proof of that previous shot and passing it into this function. So first we start by checking this isn't the first shot of a game, so we can actually call this function. Then we confirm whether or not this is a valid shot proof or not by passing the shot proof into the shot verifier function. If it is valid, we will then update the game on whether or not this was a hit. If it's a hit, we will increment the hit notch for that specific player and then emit a report event indicating we have reported the previous shot. Also, we will go ahead and check whether if this is the hit max and all the ships have been sunk, we will end the game right here. If not, we will go ahead and simply emit a shot event again. Going down to a view function, we just have a function for us to view the game state. All we have to do is pass in the ID of the game we want to view. Then we'll return the participants of the game, boards, whose turn it is, how many hits have taken place, the game status, and a game winner if there is one. Moving down to internal functions, we just have a helper here, a game over function, and unlike the left function, this does not take place when a game has been forfeited. This solely is called when the max hit variable has been reached. We've hit 17 hits, and we know one of the players has had all of their ships sunk. And this will simply confirm that this is the max hit, the game is actually over. We'll ensure that there is a winner of this game, or the winner of the game is the null address, so then we can assign a winner. We'll do that in the next step where we check who has had the hit max, and then based off that information, we know who the winner is. Set the game status to over. We make sure we clear these players from the playing mapping so we can allow them to join another game now that this one is concluded, and then finally emit the one event. So real quick before moving on, I thought it would be helpful to go through this generate contract script. And this was a script taken from the mplate starter template for Noir, but edited to a point where it's a bit more convenient when you're handling multiple circuits inside of a project. So we'll run through this real quick and hopefully be able to see some value for your own project and where you could use a script like this. But in this process, we'll also be exploring some of the Aztec TypeScript libraries in brief detail. In next video, we're going to go much more in depth when we explore Noir testing. But for now, just briefly how they can be used for the purpose of verifier contracts. But starting off, we have an array of circuits here, and we specify the name for the contract, or what we want the name for the verifier contract to be here. We specify the subdirectory within the circuit directory we can find this proof. And then also just specifying the name here for the purposes of logging so you know what step of the process you're in. But going down here, looking at our generate verifier contracts function, we're looping through each of our circuits, and for each circuit we want to grab the Acer representation of that circuit. And there's two ways we can do it. Here we can try and compile the circuit directly in TypeScript. The compile method is taken from the Noir WebAssembly package. So we go ahead, compile the program in TypeScript, and then this compiled program, it will have a value called circuit on it, and this circuit is actually the Acer representation. So we go ahead and assign the Acer variable here. If we didn't compile in TypeScript, another way we can grab the Acer is by compiling in Nargo, by running nargo compile, whatever your proof name is. And then we would simply want to read in this Acer here as a byte array, and then using the Acer from bytes method from the Noir WebAssembly package, we would then convert that to readable Acer. But either way, after this step, we will have our Acer representation of the circuit, and then we can plug that into a function called setupGenericProver and Verifier. And this is taken from the Aztec Beredenberg TypeScript package. And this will allow us to generate a prover and verifier in TypeScript. In the case of the verifier contract, all we need is the verifier, so we're not too worried about the prover. But once we have the verifier, all we have to do is call a function called smart contract, and this will give us our auto-generated Solidity code for the verifier contract. Now, one thing worth noting is that this verifier contract will always come with the name Turbo Verifier. So if you want, for the purposes of deploying it hard hat, because that's the contract deployment library we use in this case, you want to make sure you have distinct names for each verifier contract. So all we do is replace this with whatever name we specified in our circuit array above, and this line will take care of that. And then finally, once we have generated our verifier contracts through this method, we simply write them to our contract directory, and they'll be visible here. But yeah, just thought it'd be worth going over this because depending on what circuits you're working with, you could just simply use a similar method as to this, specify them within this array, and then have a nice convenient method for generating verifier contracts for each one. We also have a script in the package.json file for generating contracts, so all you have to do is run yarn generate contracts or npm run generate contracts. So real quick before the video wraps up, just wanted to document a change that was made last minute to the contract. Prior to this change, we did not have a way to prevent duplicate shots in a Battleship game, but now we have a mapping of shot nullifiers to ensure that does occur. We'll go real quick and show the use in the function. So right here, every time a turn is made, we will first check if the person who took the shot is the first participant in the game, that is the creator of the game, or the second participant, that is the person who joined the game. If they're the creator, we'll add padding of value 0. And if they are the person who joined the game, we'll add padding of value 100. Now what happens here is we serialize the shot. So we take the x coordinate of the shot, add it to the y coordinate of the shot, multiply by 10, and then add the padding to it. And using this, we're able to cover all cases of all possible shots both players could take. So in the case of the first player, they're able to take shot 0 to 99. And in the case of the second player, they'll be able to take shot 100 to 199. And once the shot has been stored in the shot nullifier mapping, we have a modifier up here called unique shot. And I guess going real quick back to the interface, unique shot will ensure that trying to find it right here, ensure that we have not seen the shot before, and if that shot's already been taken, then the contract function will revert, just to stick to the rules of the original board game.
One of the biggest questions to ask when adding any piece of decentralized technology to your stack is, what am I gaining? Or more specifically, why can't I just do this with Web 2 databases and client-server architecture? And unsurprisingly, the answer to this question is decentralization. The presence of super users or administrators is intrinsic to the Web 2 stack. So to make this a little less abstract, let's review a case of when super user risk was actually exploited. Back in 2007-2008 in the United States, there were these websites called Absolute Poker and Ultimate Bet that basically saw a cohort of players collude with someone who had super user access, or a couple of people who had super user access. And they used the administrative capabilities to view the hands of other players in their game. So essentially you have now players who can go into tournaments that are for money and have absolute domination over the competition because they can see all of the hands and know exactly how to play. In order to combat this, without zero-knowledge proofs settled on a blockchain, you have reactive laws and centralization. Similar to how we trust financial institutions essentially to escrow financial assets, where there's no trust in peer-to-peer economic interactions, the same goes by default for all hidden information-based interactions online. So this occurs in all video games, be it Ultimate Poker, Call of Duty, whatever it needs to be. There are servers running somewhere that have access to trusted information and dictate the state of the game that could theoretically be hacked and manipulated. And this extends far beyond gaming as well. Zero trust, which is the practice of trying to minimize trusted access to physical systems or reliance on a specific node or any sort of trusted access at any point in your IT infrastructure. And this is a relatively new practice, at least to the wider public domain. And it's one that zero-knowledge proofs have a huge overlap with. And as zero trust becomes more and more adopted, I think that we will see a lot of these solutions be based in zero-knowledge proofs. Our demonstration of zero-knowledge battleships is just one example of how you can wield Noir on EVM chains. It can be used to build business logic that facilitates trustless, adversarial, multi-party computations for anything you can really think of. We hope this example helps you explore the wider usefulness of applied zero-knowledge cryptography.
In the next video, we're going to be looking at Noir testing. We're going to look at a file where we test our board and shot circuits, another file where we play an entire Battleship game on-chain with our board and shot verifiers integrated, and throughout this whole process show where the Aztec NPM packages come into play, where they can be used for testing in Noir, as well as just general purpose interacting with Noir proofs in TypeScript. But that does it for this video. See you in the next one.